Hello everyone, welcome back to session 2. In the previous session, we explored what artificial intelligence is, where it's used, its history, and how AI, machine learning, and deep learning are connected. Today, we're going to focus entirely on machine learning, the technology that allows computers to learn from data instead of being explicitly programmed for every task. By the end of today's session, you will understand how machine learning works, the different types of machine learning, how models are trained, and where machine learning is used in real life. Here's what we will cover in today's session. We will answer one of the most important questions in AI. What exactly is machine learning? After that, we will learn how machine learning models actually work behind the scenes, from collecting data to making predictions. We will also explore the three main types of machine learning and understand the differences between them. Then, we will look at the machine learning pipeline, discuss concepts like features and labels, and learn why datasets are split into training and testing sets. Toward the end of the session, we will introduce some of the most common machine learning algorithms, enough to understand what they are used for. Now let's dive into one of the most important fields of artificial intelligence, machine learning. You've probably heard the term many times, but what does it actually mean? Machine learning is a branch of AI that allows computers to learn patterns from data instead of following only fixed instructions written by a programmer. Think about how we humans learn. We don't memorize every possible situation. We learn from experience. The more examples we see, the better we become at recognizing patterns and making decisions. Machine learning works in a very similar way. Instead of manually programming every rule, we provide the computer with data. The machine analyzes that data, finds patterns, learns from them, and then uses what it has learned to make predictions or decisions when it encounters new data. Now that we know what machine learning is, let's see how it actually works. Although machine learning can be very complex, the overall process follows a few simple steps. Step number 1, collecting data. Everything starts with data. Data is the foundation of every machine learning model. For example, if you want to build a model that recognizes dogs, we first need thousands of images of dogs and other animals. Step number 2, preparing the data. Raw data isn't always perfect. Some images may be blurry, duplicated, or incorrectly labeled. Before training the model, we clean and organize the data to improve its quality. Step number 3, training the model. We feed the prepared data into a machine learning algorithm. During training, the model looks for patterns and relationships in the data. It gradually improves its predictions by learning from many examples. Step number 4, making predictions. Once the model has learned from the training data, we can give it new data that it has never seen before. Based on what it learned, it predicts the correct answer. For example, it may predict that a new image contains a dog. Step number 5, improving the model. Machine learning isn't a one-time process. If the model makes mistakes, we can provide more data, improve the quality of the data, or adjust the algorithm. Over time, the model becomes more accurate and reliable. Which step do you think is the most important? Collecting data, training the model, or making predictions? The correct answer is actually data. Even the best algorithm can't perform well if it's trained on poor quality data. That's why people often say, even the best algorithm can't perform well if it's trained on poor quality data. That's why people often say, garbage in, garbage out. This means poor input leads to poor output. Garbage in, garbage out If a machine learning model is trained using poor quality or incorrect data, it will produce poor or inaccurate predictions. How machine learning works. Let's imagine we want a computer to recognize whether a picture contains a dog or not. With traditional programming, the programmer has to tell the computer exactly what to look for. For example, has 4 legs, has fur, has 2 ears, has a tail, etc. But here's the problem. Those rules aren't unique to dogs. What if the image is of a wolf, a fox, a lion? They also have 4 legs, fur, ears, and a tail. Now the programmer has to keep adding more and more rules to distinguish between all these animals. As the number of possibilities grows, writing and maintaining all those rules becomes extremely difficult. Instead, with machine learning, we don't write all those rules. We collect thousands of images of dogs and thousands of images that are not dogs. Each image is labeled as dog or not dog. The machine studies these examples and starts discovering patterns on its own. It learns what makes a dog look like a dog. Then, when we show it a brand new image that it has never seen before, it can predict whether it's a dog or not. Notice that we never told the computer a dog has 4 legs or a dog has floppy ears. It learned those characteristics by analyzing many examples. Not all machine learning models learn in the same way. Depending on the type of data available and the problem we are trying to solve, we use different learning approaches. Machine learning is generally divided into 3 main types: supervised learning, unsupervised learning, and reinforcement learning. Don't worry, we'll go through each of one with simple examples. By the end of the next few slides, you will understand when and why each type is used. Let's start with the most widely used type of machine learning, supervised learning. The word supervised means that the model is trained using labeled data. A label is simply the correct answer that comes with each piece of data. Supervised learning is a type of machine learning where the model learns from labeled data to make predictions on a new unseen data. Let's use the same dog example to see how supervised learning works. For example, if we are teaching a model to recognize dogs, we provide thousands of images and each image already has the correct label, either dog or not dog. The model studies these examples and learns the relationship between the images and their labels. Once training is complete, we can show it a new image it has never seen before, and it will predict the correct label based on what it learned. In other words, during training, the model already knows the correct answers. Its goal is to learn how to produce those answers on its own when it sees new data. Common applications of supervised learning. Spam email detection. Imagine we have thousands of emails. Each email is already labeled as either spam or not spam. The model studies these emails and learns patterns. For example, spam emails may contain suspicious links, certain keywords, or come from unknown senders. When a new email arrives, the model predicts whether it's spam or not based on what it learned. Disease prediction. Hospitals have medical records from thousands of patients. These records include information like age, blood pressure, symptoms, and test results. Each record is labeled with the correct diagnosis, such as whether the patient has a particular disease. The model learns the relationship between the patient's information and the diagnosis. Later, it can help predict whether a new patient is likely to have that disease. Note, AI assists doctors, but it doesn't replace them. Machine learning is used to assist healthcare professionals by providing predictions and insights. The final diagnosis and treatment are always made by qualified medical professionals. House price prediction. Suppose we have data about thousands of houses. For each house, we know its size, number of bedrooms, location, and its selling price. The selling price is the label. The model learns how these features affect the price. Then, when we enter information about a new house, it predicts its estimated value. Credit approval. Banks have records of previous loan applications. Each application includes information such as income, employment status, credit history, and existing debt. Each application is labeled as either approved or rejected. The model learns from these past decisions. When a new application is submitted, it predicts whether the applicant is likely to qualify for the loan. Again, banks often use AI to support human decision making, not to make the final decision on its own. Did you notice what all these examples have in common? In every case, the model is trained using data that already has the correct answer. So in supervised learning, we already know the correct answer during training. That's what makes the data labeled. The model learns by comparing its predictions to the correct answers and improving over time. But what happens if we don't have labels? That's where unsupervised learning comes in. Now let's look at another type of machine learning called unsupervised learning. Remember that in supervised learning, every piece of data had a label. The model already knew the correct answer during training. But what if we don't have those labels? That's exactly where unsupervised learning is used. Instead of being told what each example represents, the model receives only the data. Its job is to analyze that data and discover patterns, similarities, or groups on its own. How unsupervised learning works? Let's continue using our animal example. This time, imagine we give the model hundreds of animal images, but none of them are labeled. The model doesn't know which images are pandas, tigers, and birds. Instead, it looks for similarities between the images and automatically groups similar animals together. Notice that the model creates the groups, but it doesn't know their names. Humans can later look at those groups and say, this group contains dogs, or this group contains lions. Applications of unsupervised learning. Customer segmentation. Imagine a supermarket has information about thousands of customers, such as their age, shopping habits, and how much they spend. The data isn't labeled as student, parent, or business owner. Instead, the machine learning model analyzes the data and groups customers who have similar shopping behaviors. The company can then use these groups to create personalized advertisements or special offers for each group. News article grouping. Imagine a website has thousands of news articles, but none of them are labeled by category. The model reads the articles and looks for similarities in the words and topics they discuss. It may automatically group articles about sports together, technology together, and politics together, even though no one told it what those categories were. Anomaly detection. Sometimes the goal isn't to create groups, but to find something that doesn't fit with the rest of the data. For example, a bank may analyze millions of normal transactions every day. If one transaction is very different from the others, it may be flagged as unusual. This is called anomaly detection. because the model identifies data that doesn't follow the normal pattern. Photo organization. Imagine you have thousands of photos stored on your phone. The model analyzes the images and groups together photos that look similar, such as pictures of the same person, similar objects, or similar places. It creates these groups automatically without being told who the people are or where the photos were taken. Did you notice the difference between these examples and supervised learning? In supervised learning, the model already knows the correct answers during training. In unsupervised learning, there are no labels. The model explores the data on its own to discover patterns, create groups, or identify unusual behavior. The third type of machine learning is called reinforcement learning. Unlike supervised learning, there are no correct labels, and unlike unsupervised learning, the model isn't trying to group data. Instead, it learns by interacting with an environment. Think of it like learning through trial and error. The model performs an action, receives feedback, and uses that feedback to improve its future decisions. If the action is good, it receives a reward. If the action is poor, it receives penalty. Over time, the model learns which action can lead to the highest rewards and begins making better decisions. Imagine we have a robot inside a maze. The robot doesn't know the correct path. It starts moving one step at a time. If it moves closer to the exit, it receives a reward. If it hits a wall or moves farther away, it receives a penalty. At first, the robot makes many mistakes, but after many attempts, it learns which path gives it the highest reward and eventually reaches the exit much more efficiently. Now, applications on reinforcement learning. Game playing. AI systems can learn to play games like chess by playing thousands or even millions of games, learning which strategies lead to winning. Self-driving cars learns to make better driving decisions, such as staying in its lane, avoiding obstacles, and following traffic rules. In practice, these learning often happens in simulations before being used in real vehicles. Robotics. Robots can learn tasks like picking up objects, sorting packages, or navigating through a warehouse by improving through repeated practice. How did you learn to ride a bicycle? Did someone upload the instructions into your brain, or did you learn by trying, making mistakes, and improving? Exactly. That's the basic idea behind reinforcement learning. The model learns through experience and receiving feedback after each action. Before a machine learning model can learn, we need to understand two very important terms: features and labels. Features are the piece of information that describe something. They are the inputs we give to the model. For example, if we want to predict the price of a house, we might use features such as the house size, the number of bedrooms, and the location. Label is the correct answer that the model is trying to learn or predict. In our house example, the label is the selling price. The model studies many houses, learns the relationship between the features and the price, and then predicts the price of a new house. Another example, let's go back to our dog example. The features might include characteristics of the image, such as the shape of the ears, the body structure, the fur pattern, and many other visual details. The label is simply dog or not dog. The model learns how those image features relate to the correct label. Features equal input information. Label equal correct output. If you want to predict whether an email is spam, what do you think the label is? The correct answer is spam or not spam. The features could include things like the sender, keywords in the email, whether it contains suspicious links, and other characteristics. The label would be spam or not spam. Now that we know what features and labels are, let's see how we use our dataset. When building a machine learning model, we usually don't use all the data for training. Instead, we split the data into two parts. The first part is called the training data. This is the data the model learns from. It studies the features and labels, discovers patterns, and builds its knowledge. The second part is called the testing data. These are examples the model has never seen before. We use this data to evaluate how well the model performs on new unseen data. This helps us understand whether the model can generalize instead of just memorizing the training example. Let's go back to our dog example. Imagine we have 10,000 labeled images. We might use 8,000 images to train the model. The remaining 2,000 images are kept aside and not shown during training. After training is complete, we test the model using those 2,000 new images. If it correctly identifies most of them as dog or not dog, we know it has learned useful patterns. Why not use all the data? You might wonder, why don't we just train on all the data? Because then we'd have no way to check whether the model performs well on a new clean data. So far, we've been saying the model learns, but how does it actually learn? The answer is through machine learning algorithms. An algorithm is simply a set of rules or steps that tells the model how to learn from data. Different algorithms are better suited for different types of problems. So there isn't one algorithm that's best for everything. Let's look at some of the most common machine learning algorithms. Linear regression. Linear regression is used to predict continuous numerical values. For example, predicting the price of a house, tomorrow's temperature, or a student's exam score. The output is a number, not a category. Decision tree makes decisions by asking a series of questions. Does the customer have a high income? Do they have a good credit history? Based on the answers, it follows different branches until it reaches a final decision. It's easy to understand because it works similarly to how humans make decisions. K-nearest neighbors. KNN classifies new data by looking at the most similar examples. Imagine moving to a new neighborhood. If most of your nearby neighbors speak French, you might guess that French is commonly spoken in that area. Similarly, KNN looks at the nearest neighbors and predicts based on them. SVM, support vector machine, tries to separate different groups of data by finding the best possible boundary between them. For example, separating emails into spam and not spam, or images into dog and not dog. Neural networks are inspired by the structure of the human brain. They are especially powerful for complex tasks like image recognition, speech recognition, language translation, and many modern AI applications. Deep learning, which we will study in our next session, is based on neural networks. Each algorithm has its own strength. The best algorithm depends on the type of data and the problem you are trying to solve. For example, if you wanted to predict the price of a house, a common choice would be linear regression because the goal is to predict a numerical value. Machine learning uses different algorithms, and each one is designed for a different type of task. Even after training a model, things don't always go perfectly. Sometimes the model doesn't learn enough. Other times, it learns too much. These two situations are called underfitting and overfitting. Underfitting happens when the model doesn't learn enough from the training data. As a result, it can't recognize important patterns. Because of that, it performs poorly on both the training data and on new data. Overfitting is the opposite. Here, the model memorized the training data instead of learning general patterns. It performs extremely well on the training data, but struggles when it sees new unseen data. So the goal is to train a model that learns the important patterns without simply memorizing the data. That brings us to the end of today's session. See you in the next session, where we will dive deeper into deep learning and neural networks.